Welcome back, everybody. We're going to return to regression, and this time around, now that we've introduced the topic of loss functions, we can see how changing a loss function or changing the features or the way the weights work in a particular regression can give us very different kinds of results. So let's dig into it. More and more and more regressions. There we go. So remember, we've been talking about, in the last lecture, we were talking about the idea that machine learning really is just optimization, right? We've got a training set and a test set, and what we want to do is do really well in general, no matter what the problem is. So ideally, we want to be doing great on that test set. But the way we can try to do better in general is to minimize our errors on the training set. And what are we minimizing? We're minimizing some function, right? So we know that the best weights in general are going to be weights which we can pick which will minimize some loss function, some definition of error. Okay? And that's the loss function or the objective function or the error function. It all depends on who you're talking to, but we're always talking about the same thing there. So it's important to remember that the model and or the algorithm or whatever it is that we're working with is a combination of both the nature of those weights, the form that they're in, and also of the loss function which we are picking to get the quote-unquote best weights. So again, as we've said before, machine learning is really just picking an appropriate model and then minimizing a loss function to get the best version of that model. Now, there's a lot of ways you can find that best W, that best weights, best set of parameters. You can just do some good old-fashioned search. So there is different ways in which we can either just take the entire space of weights and go after it completely or go after it in a regularized grid fashion. We can try to use techniques where we think that we're going to do better if we move this direction through the weight space towards a particular thing which is going to locally minimize our problems. There's various kinds of numerical methods, essentially, lots of algorithmic search or ways in which you can numerically search. There's also completely different ideas where you could just try to use stochastic processes. Genetic algorithms are a form here where you are just trying to probabilistically find the best parameters. But we've already looked at regression in terms of ordinary least squares, and it's one of the places where there's an analytic or closed form solution to your loss function where you can just solve for x, or in this case solve for w, right? And basically, as long as the loss function that you are trying to solve, right, has some sort of convex shape to it, then we know that there exists some point which is able to be the one true and only minima, the global minima, and that means that we can analytically solve for this just as long as this function has this convex shape, right? And you'll remember from just super quick review that the shape is convex if you can pick any 2 points, W0 and W1, and everywhere, when you draw a chord between those 2 points like I just did, if everywhere that lies on the line, the loss function between 0 and 1 is at or below the location of the chord, then this thing is convex. All right, so any convex function has an analytic closed form solution, at least up to a certain point, because there's some matrix algebra problems that you got to solve too, but all right, at least theoretically. So let's just go back to that, what we call univariate linear regression using ordinary least squares. I'm just going to recap in a slightly different way what I covered, what was it, 3 lectures ago? Okay. So, as always, we have some sort of training set, right? Whoops, go away. I want highlighter. All right, so we have a training set, and each one of those points that we have that's an input also has attached to it a true label, something that we want it to be. In this case, rather than bird or not bird, like we were doing with classification tasks, the true label is a number that is somewhere in the reals. We're trying to predict an output value, predict a y given an x, right? So we've got a set of inputs, x's, and we've got n samples in our training set. So we're going to fit a line, which has got, y is equal to mx plus b, right? So we've got our bias term and our weights on x. And we know that what we are trying to do is we're trying to find the weights that minimize the error, right? Because remember what this y is, this is the value we should be predicting. But this is the value our line of regression is. So just to draw something, so if we have some dots and we have a line that we are fitting through those dots, then these distances in here are this value, right? So this is the predicted right here. This is the stuff that lies on the line of regression, that lies on that red line. And this is what the value should have been right here, right? So all those distances are expressed here, and they're not just expressed there as a distance, but they're expressed as a squared distance, right? What happens when you square something? First off, negative things disappear, everything's positive. Okay, so squaring says we don't care which direction off the line we're off, what matters is how far off we are, right? And that square also means that points which are way off the line and have a big error have a very large influence. Okay, we'll come back to that. All right. So we have some lines we're fitting, and right, we've kind of already said this stuff. We're fitting stuff of the format right. So we're fitting things of the format that we've already established, where our inputs are a 1, the bias term, and an x. And we know that what we're doing is we're minimizing this squared, okay? We can rewrite that, single line version of what we're doing, right? Where we're iterating over every dot y, okay? And we're going to, write it like some sort of iterative function. We can recouch that into matrix algebra, right? So we can rewrite that with capital X being the design matrix. And to understand the design matrix, you should go back to the first regression lecture, okay? So, and y is our set of desired outputs. So we're going to solve this problem all at once for the whole data set, right? Because this formulation says we're going to sum over every point and find something. This kind of math notation says we're going to use a matrix to represent all of our data all at once, and we're going to solve for everything in one go. Okay? So all of the data is here in X, Here are our weight parameters. All of the training labels we want is there in that y. And this is just the square, right? Because right here, this is xw minus y quantity squared. Well, in matrix land, when we do squares, we have to transpose one of them, okay? And that's to make the size of the matrices line up correctly. So we have the output minus the true value squared, but we're writing it here in matrix versions. All right, so this is the thing we want to minimize, is this quantity. And when we make that quantity by picking a w that makes that quantity as small as it can possibly be, we have the best possible w's to represent everything. All right, so so we can start over again here, right? This is what we just wrote. We are in matrix notation now. Well, how do we solve for ordinary least squares? How do we show that we can solve this exactly in an analytic way? Well, this is just a FOIL, a bit of algebra, right? It's just matrix algebra. So we can expand it out. xw times xw, xw times minus y, and so on and so forth will expand out the terms of the FOIL. All right. Now remember, what we're trying to do, let me draw again, is that we want to set that there's this global minima, this bottom, this weight, which is going to give us the very bottom of the loss curve. Okay? Well, how do we know when that loss curve when the bottom of that loss curve is found? Well, this is the tangent line right there. So that's where the partial of loss with respect to the weight is equal to 0. Okay, so we're looking for that. Well, we better take a partial of what we did just a second ago. So we take the partial of this with respect to weight, because we're trying to find where we have that 0. And when you've got it down to here, right, then this is just going to be rearranged to find this form, which is the closed form solution. All right, so that's where we got to. Just a quick note to remind everybody, right? This is a term right here, which is squared in W, okay? Because this is W transpose in W, so this is a W squared term in matrix land. And that's why the derivative of this term here is 2 of everything times W, right? Because W squared, the derivative would be 2W. So that's what we've got there. Okay, so we've gone through everything that we actually did in the last go. Let me just kind of throw a worked example at you, okay? I don't want to spend very much time on this, but this is here in the slides if this is the kind of thing that helps you think, right? So if we have an actual training set where all these little dots here are represented, right? So here's 1, 1, here's 3, 1.9, right there. Here's 2, 1.5, right? So this is our data. And remember, what we're doing is we're trying to fit a line right here of the form xw. So we can just look at each one of these data points here, right? Each one of these data points, 1, 1, 1.93, etc., etc. So because the assumption here is that these dots are corrupted by some noise, some real process lies underneath it, but there's some noise screwing them up, right? That's the way linear regression math works, is it assumes that there's a bit of normal distributed noise on top of stuff. Well, because of that, we know that if we solved for these values of W0 and W1 on any two of these points, we would get a particular value of W0 and W1. But we wouldn't get exactly the same value if we picked two different points, because there's noise in the system. And that's exactly what we're trying to minimize, is minimize the discrepancy between all of the points in the line. All right. So matrix notation time, we can just plug those numbers in, right? And we can do the math and come up with a solution using this closed form that we were just talking about. Okay? So like I said, I'm not really going to go into details, but if you like this kind of stuff, there it is. So now we get to do something actually new instead of just a recap of a couple of lectures ago. So we don't have to do just straight lines with least squares. We can do more interesting curves. And that may seem a little bit weird because we've kept talking about least squares as a method which is linear. And you're like, well, it must fit the linear data, but no, sir. The thing that has to be linear is the parameters. We don't care about whether the x's are linear. So we can fit anything of this form, right, where we can go ahead and have squared terms in x or however many polynomials we want, okay? As long as the weights are all linear, everything works just hunky-dory, okay? So here are the same data points on the left side and the right side. And what we've been doing is we've been fitting a line through those points. But maybe it's not a line. Maybe it's something a little bit more complicated, like some sort of polynomial. So, how would we do that? Well, again, it looks a lot like what we just did, except this time the weights are now not just, last time around we had y is equal to, right? So that's the comparison between the two. So it's the same up to this point, right? This is what we were doing. Now we just add on more weights. The weights are always just w, right? There's no w squared or something like that. That's the key here. But the x's can be whatever they want. And then we can fit polynomials on top of a linear parameter space. So again, we are linear in terms of the w, right? This is still a function, an equation, the prediction of looks like this. It's just that the x's now look like polynomial features. Back up! I said polynomial features. Loads of you were confused during the regression lecture a couple ago when I showed in the demo this polynomial features thing. Well, this is where it's going to come in, right? So we can take any given x input and we can make it squared or cubed or whatever. We just take the number and we throw it into the feature space. All right. So everything looks about like, well, it looks actually not about like, it looks exactly the same. So we do exactly the same ordinary least squares. We solve for the equation in exactly the same way, and the closed form solution is exactly the same. The only thing which is changing to do polynomials is the x input. The x input now to do a third order polynomial, right, to do something like this, where it's wx plus w2 times x squared. We now have 3 variables. And so our x matrix is 3 wide now, whereas in the past it was 2 wide. All right, so again, you can take a look at that at your leisure, or leisure if you're British, but it really is identical. It's just that the x design matrix has changed. So everything is really hunky-dory. I'm going to burn through this slide because it really is the exact same thing. We haven't changed anything except the format of the x and the w. Other than that, we solve for it in the same way. There's the same least squares solution. This is identical to the last version of this same slide. Oh, and the last time around, I forgot to note that there is indeed a little bit of Python here for you. Again, this was also in a couple of lectures ago. This is just how you can use NumPy or NumPy to compute this quantity. Okay, so one more kind of regression that I wanted to give you a chance at, because now that we're expanding the size of the X design matrix to more and more variables, it doesn't have to be X squareds, it could be more variables. Okay, so it is often the case that what we're looking at is we're looking for some sort of way to predict a given output based upon multiple inputs, right? Maybe it's not just birth weight from estriol, but birth weight from estriol and mother's height, right? Something like that. So we can do exactly what we've been doing. It's just that now these x terms will represent multiple different independent variables, not just x and x squared and x cubed. Okay, so in this form, we have a bias term plus the w1x1 plus w2x2 all the way up to however many m features we have. And those features could be, well, the iris data, right? The iris data has 4 measurements. By the way, if you didn't know, the iris data is actually about iris flowers. And they're measurements of like the sepal width and the flower length. And I don't even remember what the other 2 are, right? But they're measurements of a flower. So we have 4 separate measurements of the flower. And that would be, x1, x2, x3, and x4. Right. So, at any rate, we can do the same thing now in multiple dimensions. Now we are not fitting a line, but we're fitting a plane if we're doing 3 dimensions, right? A y and 2 x's. And this generalizes again to a hyperplane if we're doing even more dimensions. So let's give you the worked version, right? Now your inputs look like this. There are 3 inputs for every data point, x1, x2, and the desired output y. Okay? And we can write it in the same matrix form because it's still a linear combination, right? The y value is going to be a linear combination of the x's going into it. So we can just plug these numbers that are at this row into here, and each individual data point can be fit. Because there are 3 unknowns in every line, to solve for a plane we will need at least 3 data points, clearly, right? 3 equations, 3 unknowns. But because there's way more than 3 points, and we know there's some noise in the process, we know that any given set of 3 of these points is going to give us a particular value for the w vector, but each set of 3 points will give us a different value. So again, what we're going to do is ordinary least squares, which is going to try to minimize the error between wherever that plane is placed and all those data points. And it's going to minimize the error, and when the error is a squared error, just like we keep talking about. Okay, so now your variables look like this. We've got 3 variables in the x and 1 in the y. And we are, by the way, again, the reason there's 3 variables here is there's a bias term and x1 and x2, right? So we can solve for W using the same ordinary least squares analytic solution that we've always been doing. So, same math. You can just decide which thing is best for your data. Okay? So again, we've been evaluating something as by its error on a set. So on the training set that we're fitting to, right? These are the training set errors. This is a measure of, after we've done the best we can do, what are we able to look at on the training set, the set we're using to create this algorithm, to create these parameters? How good are we doing? How well have we fit? And in some sense, this kind of a value tells you potentially which one of these models you kind of like the best for your training data, at least, right? Which model fits the training data the best? But remember, that's not the same as generalizing to new data, because the training data will always have unique patterns in it due to the noise. All right. So, all these things, they're all the same. The math is really the same, and especially you can see that when we go away from a notation like this, and we take it to a notation like this, where we go to that matrix notation. This is why we do everything in matrix land, okay? Because it's really, it shows you that we're just doing the same thing. The only thing that's changing is the exact form of this X and W, what those numbers represent, what the different columns are. But the math stays the same, and that's the key. The only thing we care about is if all of this is linear with respect to those parameters. And if it is, we have an analytic solution. So let's just recap everything. Our intuition is that we're trying to fit a loss function. We're trying to make that loss function be the lowest it can possibly be. And we make it the lowest it can possibly be by setting these parameters to minimize, in this case, the error between the fitted line or plane or polynomial and each individual noisy data point, okay? And we do that over all the noisy data points. We're minimizing the whole set, okay? The error with respect to the whole set. And what we're minimizing is, once again, that squared error. All right, so the nature of all this, is that it's very easy to implement, and it's a very generic implementation, and the same bit of code can function for all the various examples we've thrown at you so far. Well, let's throw an example at you that it doesn't work for. All right? So let's talk briefly about robust estimation. Robust estimation is the idea that you have some data points, and maybe there's an underlying structure here, but maybe some of these data points are what we call outliers. So it's not just the usual thing where there's a process with some noise, but somebody threw an orange into the middle of all of your apples, okay? So there's one data point that's like way out here, and this is your outlier, okay? All the rest of them, we could fit some line on them that was relatively cool, but this outlier way the heck out and gone is going to mess up your fit. Okay, so typically in the real world, an outlier exists again because you thought you all had apples and suddenly an orange falls in the machine and the orange gets measured. Okay, it's going to be something exactly like that. So it can be hard to detect oranges. They're in the machine. The machine doesn't have a special way to detect oranges versus apples. You're just making measurements of it. Okay, so how do we deal with the case when our data might have outliers in it? Well, one thing to do is to use techniques that are called robust techniques. They're robust to a few outliers. That's what the word means. It means you can throw a few bits of craziness into the system and it won't break the system. There are a bunch of ways to do this, and there's whole fields of statistics and machine learning and even things like control systems theory and signal processing, which also deal with statistical outliers. Well, one of the things you can best do is to change the way in which you're using an error metric. Okay? Our error metric that we chose previously had a squared term in it, right? When we were trying to fit the line to the square of the error from the real values, right? But if instead of using the squared, if we just use the absolute value, now those outliers don't trouble us so much. Why is that? Well, if you take a large number and square it, what do you get? A ridiculously large number, right? So in something which has a squared term in it, we get an outsized influence by outliers. A single outlier can pull the solution pretty far away, whereas when we don't have a square in there, then we don't have such a big outsized influence by a single way out there point. Now, remember, however, we do need to get rid of negative signs. We don't care if we're only trying to minimize the error. We don't care if the error is from a point being below the line or above the line, whether the value is positive error or negative error. So we have to use the absolute value in that case. So these are called various different things. You can see here that this is called an L2 norm or an L1 norm. And it's been a few years, but if I remember correctly, that L is for Lyapunov, that Russian mathematician. And the idea is that L norms are written like this. Okay, so this is like just a standard notation you will see. So this is an L1 norm, and this is an L2 norm. And obviously you can have, L sub n norms, so you can have anything. And that n, that thing, is an exponent. So if you had an L of n, that would be this. Okay? But at any rate, that's getting beyond the scope of what we're talking about right here. I'm just giving you kind of some generic math if you haven't already seen this sort of notation. Okay. So again, the difference between L1 and L2 is just L1 is an absolute value function and L2 is the error squared. So what if we minimize not the mean squared error, the L2 norm, but if we minimize the L1 norm, or the what's called the mean absolute error? So I should have gone backwards over here, right? So another thing you can call this is mean absolute error and mean squared error. So scikit-learn actually does this. It calls it MSE and MAE. Okay, but it's all the same. The 2 norm and the 1 norm. All right. So here we are. We've got two different cost functions, one of which is squared. There we go. One of which is squared, and one of which is just an absolute value. But we can do the same thing. We can solve this very general form where we just say what we're trying to do is we're trying to minimize the result of applying this cost function across every single data point that we have in the training set. Okay? Or, obviously, we can take it into the matrix notation, right? We've shown that. So in the squared term, our regular version of what we've been talking about over and over again, this crazy outlier has a very big influence, and it's pulling this line away from everybody else and towards itself. But in this case, fitting that, we're going to end up fitting this much less influence. The line is much closer to this group of points. So, again, here's the L1 norm, and we can do that, as I was saying just a second ago, in matrix notation. So we just go ahead, take that line-by-line version of it, and we can write a cost function and obtain the gradient. Okay, well, so what are we doing here? Well, the problem is this, right here, that this thing is now no longer perfectly differentiable. And that because it's not differentiable, there's not a closed form solution for it anymore. So instead of just solving for W all at once, given the x values, we can try to piece by piece follow the evidence from each data point that we go in. So how does that work? Well, we have these all here. We can write the regular old OLS version of this, right? Where what we're doing is we're doing this mean squared error minimization. But we know that that's going to, if we put in an outlier, this 0.6, right, we pull everything way off those lines that already existed. So instead, we can minimize this error, which is going to pull us right back down over here. So the problem here is that when you take the derivative of the L1 norm, okay, right here, this is the L1 norm of some function, then the L1 norm has this form, right? The derivative of it is the derivative when we're greater than 0. When we're less than 0, the derivative is the negative derivative. And when we're exactly 0, it's 0. So if I drew this out, what we would see is that the derivative is going to have this kind of form, which is convex but not differentiable at this point down here where we get to the 0. So that's why it's not something that we solve in a closed form. And anytime we can't solve something in a closed form, the way that we can do it is that we can take at any point that we're interested in, we can figure out the direction that will take us towards a minimum. So we want to go that way. We don't want to go, let's use yellow, that way. That's a bad direction to move. We want to move that way. So every data point that we get, we can bump the thing a little bit towards where we think the minimum is. So that is the nature of what a gradient is. So the gradient of the one norm is the sine function. The sine function just says whatever's inside me, take the sine. Okay? So the derivative of, again, is exactly this. The derivative of the one norm is the sine, which it gives you either the plus or the minus here. And then everything that was left over is still left over. And that's why its partial derivative looks like that. Okay? So, oh yeah, there we go. There's my definition of sine. Sine is plus 1 when the value is greater than 0, minus 1 when it's less than 0, and exactly 0 when it's exactly equal to 0. So the derivative of the one norm is sine of f of w times df of w dw. Okay. And again, the way we do it intuitively is that wherever we're at, we move towards where the minima is, at least a little bit. Okay. And how much you move is a big deal. And that is controlled by this parameter lambda here. So every time we want to update the weight, we update it from where it was, right here. We update it a little bit towards the minima. And how much we update it towards the minima is controlled by that lambda. That lambda is a number that's always less than 1. Or I should say between 0 and 1. Okay. So that, by the way, is a preview of things we will be doing a lot. Gradient descent. And it gets applied to a lot of things. So we can work the numbers again one more time. Where am I at for time? We're getting pretty bad. So we're just, again, we can throw these numbers in here. And now they're with that outlier, you can work these numbers, update your gradient some small amount according to whatever lambda you have, and do it iteratively over and over again until it converges, and you get the same thing. So that last one was about being robust to outliers in your data. However, there's another kind of robustness that we might be interested in, and that's being robust to your model being too powerful. When your model is crazy powerful and your data is rather simple, when you're trying to fit a ninth order polynomial onto linear data, then you can end up in quite a bit of trouble. So we can try to be robust to the model as well as to the data. And that is going to be another short video where I'm going to show you a Jupyter notebook. Oh, wait, actually, did I set it up? Let me try to do it all in one really quick. I didn't set it up, but I can. Right. Please say that I can do this super fast because I would rather. Yes. Woohoo. All right. Let me very quickly make this a little bit smaller so that we can see it all. Great. Okay. Perfecto. All right, I don't have to do separate videos. I'm so smart. Okay, so now what I wanted to show you is how to do polynomial regression and regularization with respect to the model degrees of freedom. So you saw this same notebook format a couple of lectures ago. Once again, we're going to create some toy data, and we can fit any kind of function that we want to make this toy data. So I'm going to fit a sinusoid, okay? So a sinusoid, as you may remember, goes up and down and up and down. In this case, it's just one full run of a sine wave. So when we take that data and turn it into the features that we were talking about in the past, right? Here is the bias term, that first column, and here is that sine wave going from 0 up to 1. Okay, so I can fit to this any kind of number of polynomials. Okay, so remember what we were just talking about, right? We can make a fit of a polynomial using linear regression. And to do that, all I need to do is make my x inputs be both the x value itself on this middle column and the x value squared. Okay? We can add in the cube as well. Oops, only if I can type correctly. Right? So now we have x value, x squared value, and x cubed value. Pretty simple, huh? All right, so doing that, we can fit different orders of polynomial curves on the same data. Now the data, remember, is a sinusoid. Okay? So just like before, we have this green truth. This is the real sinusoid, which is going to be fit here. Okay? This is a real underlying function. And the values here are corrupted by noise. So that real value, when we draw a random sample from it, is going to be corrupted by random Gaussian noise up and down. So the same data is being fit here 4 different ways. It's being fit by a 0th order polynomial, which, as we said the last time, is just what? That's right, it's just fitting the mean of the data. It's fitting a constant, and the constant it fits is the mean y value. The mean y value of a sine wave is 0. So it did a good job there. We can fit a line on that sine wave, and it doesn't look very good. But as you may remember, any kind of sinusoid can be approximated by an infinite series of polynomials, right? Pretty sure I remember right that that's called a Taylor expansion. But if I got it wrong and it's the other one, it's been a while since I took calc. All right, so we should be able to fit a sinusoid with a higher order polynomial, is what that says, right? That's the whole idea. Well, a 3rd order polynomial doesn't do too shabby, right? Goes up and down. And a 9th order polynomial does pretty crap, right? It's the 9th order polynomial, because there's only 10 data points here. It has enough degrees of freedom to exactly fit every data point. So the 9th order polynomial is running exactly through these data points. There is 0 error here on the training set. But generalization is going to suck. Okay? How we can show that to you. So now we can take these exact same training data set, the exact same polynomials, and now we can draw 50 new samples from the same sinusoid corrupted by noise. So we're going to call these validation, okay? Validation sample, validation set. And you can see here in the yellow are these new 50 draws from the same sinusoid plus noise. There in blue are the original training set that we drew a while back. That is what we used to fit the algorithm. Okay? So you have the same polynomials, 0th order, 1st order, that is a line, 3rd order, 9th order. And you can easily see that the 3rd order is going to generalize relatively well, and the 9th order is a pile of steaming horse poop. Well, we don't have to just use our eyeballs, okay? We can actually measure how bad a situation we're in. Okay, when we have a validation set or a test set, what we want to see is that we can run the algorithm on the training set, get the fixed form of the parameters, and then we can run predictions on a validation set, and we can see, what is the error? And if we want to pick which one of these lines, which one of these curve fits, right? Which one of these curve fits is the one we want to use in the future, we can just say whichever one has the least error on our validation set on these yellow dots, that's the one that is the curve for me. All right. So to evaluate the validation error, we are going to do a root mean squared error. A root mean squared error is, oh sorry, this is actually a mean squared error, isn't it? Yeah, it's a mean squared error. Ha ha ha. I'm not going to change that because it'll cause everything to error out. But it's a mean squared error, so that's just the same as what we've been talking about, right? It's the square of the error. All right, so what are we trying to do here? What we are trying to do is we're going to plot for every degree of polynomial how much training error we've got and how much validation error we've got. Remember that the training error refers to how close are you to the blue points. And remember that the validation error is how close are you to the yellow points. So for a third order polynomial, it's about the same. When the line of fit here, the red, is about as close to the blue as it is to the yellow, on average. For the ninth order polynomial, that is not the case. It is very close and in fact right on top of the blue, but its error to the yellow is actually quite extreme. All right, do we see that here? So the training error goes down, 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 down. So every step you take getting a more and more complex fit, the training error goes down. But on the validation error, the yellow dots, the error only goes down to a certain level, and then once the polynomial gets very complex, as it goes past 5, 6, 7, 8, the error is going up again. It's not generalizing as well. So we get more and more goodness of fit on the validation set as we get more complex of a curve, but at a certain point, the complexity is enabling us to overfit to the noise in the training set and be too good at the training set data, which is just a random draw anyway. Okay, so that's what this curve shows you. When you see that both training and validation error are going down, you know that your model can be more complex. And when your validation error starts to go back up as your model complexity increases, that means that your model is now more complex than the data set, and you're overfitting. Well, as I promised you, there's another robust estimation technique that we can use. One which, instead of trying to penalize bad data, penalizes bad models. Okay? So this is often called regularization in this form. We have the same loss function that you are used to. There is the OLS loss function that we've seen over and over again. But now we add not that part, but this part is all brand new. You've never seen that. What is that? That's the L2 norm of the weights. The L2 norm of the weights, well, what does that do? Well, what it says is, as the weights or the parameters get very, very big, we're saying that we're doing worse, right? We want to minimize loss. We want to make sure that the total of this function L is as small as it can be. So when my parameter values get large, that means I'm doing worse. What this is doing is it's actually trying to squeeze the weights down. Okay? Every time a particular weight grows really, really big because it's really good at making this whole thing work, then it's going to take all the other weights that are not big and it's going to squeeze them down. Okay? So overall, the squeezing is done proportional to the square of the weight size. That tells you something. So big weights are highly penalized. And we're going to, again, it's about the total amount of weight. Okay? So if one weight really has to be big in order to make this function work, then it's going to get big and all the others are going to get squished. If all of them need to be a little bit big, then that can be an equivalent overall amount contributed by this right-hand term. Okay? On top, so that's the 2 norm of the weights, and that is an L2 regularization. Okay? So this lambda in front is just a coefficient that governs how important the regularization is compared to just fitting the damn thing. Okay? So because, is this still quadratic in W? Yes, it is, right? Because this is a W squared term, essentially, right? You can see that right here. So because this is a W squared term, it's just another quadratic. And because it's a quadratic function, we know that it is a convex curve, and therefore it has a closed form solution. And if you would like to, you can derive this yourself using this and going through the partials of L and so on and so forth. Okay? So you can plug this into NumPy and you can solve for a regression. And that, again, that lambda, when that lambda term, oops, my apologies, when that lambda term is a large value, a value close to 1, then we have a lot of squishing of the weights. Okay? When that lambda value is a very, very small number, then this whole right-hand thing disappears, and we just end up back in ordinary least squares, right? If this number is approaching 0, the lambda, it's approaching 0, then the right-hand term disappears. So when lambda is tiny, 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 much less than 1, it's just OLS. And when lambda is approaching 1, it is highly penalized for the amount of each parameter. Okay, so we can go ahead and show you how this works. Ridge regression is another name for L2 regression, or you can call it Tikhonov regularization, or a bunch of other stuff. But don't call it late for dinner, as the old joke goes, right? All right, so ridge regression is something we can grab out of sklearn. So you could go in and do this in NumPy instead, but we're just going to do it very fast. Okay. So this is all a 9th order polynomial. Oops. I should have said this. And I should have been careful when I was typing. All right. So these 4 panels are all this 9th order polynomial that you've already seen several times now, right? And we know that when lambda is 10 to the minus 9, it's a value getting very small, very close to 0. What we get is the same OLS solution that we did previously. And as we make that number a little bit bigger, 10 to the minus 6, we get something quite reasonable out of our 9th order polynomial fit, which previously had been a pile of steaming crud. Okay? And as we make that lambda closer to 1, 10 to the minus 3, or 10 to the minus 1, now we are squishing those weights and making the 9th order polynomial, which is way too powerful, right? We know that for a fact. Way too powerful is now being squished down. We're adding bias to the situation. We're pushing the weights of the algorithm to strongly prefer to be in a particular form. The regularization pushes the algorithm towards a squished out set of weights that are essentially going to all be the same. Okay? So we're adding bias to the system and removing variance, that bias-variance trade-off, right? There's too much variance every time we get a given training set. And a ninth order polynomial can take a 10-point training set and fit it perfectly. Sorry, almost perfectly, right? And because of that, it's way too powerful. It has too much variance. It's caring too much about the variance in the training set. Okay? When we add bias to the system by putting in a regularization term to shove it towards a particular preferred format, to a squished out version of the curve, then we are removing that variance. Okay? So that's what I wanted to show you. Remember, we talked about two separate kinds of regularization. Of robust estimation. Robust estimation number 1 that we did back in the slides is robust to outliers in the data. But this is robust to your algorithm being too powerful. Okay? And the regularization method squishes the weights down, trying to keep them from getting out of control. And it adds bias to the system, trying to keep the overall solution found in a particular form. All right. So thank you very much for your attention. I know that I went way over. I'm afraid to check. Well, just a few minutes, actually. So not too bad. Thanks for sticking to the bitter end. I will talk to you at office hours or the next lecture. Bye. Oh, and Magic says bye too. He's been over here licking himself as he's asleep. Yes. Come over here. Say bye. Do you want to press the button to stop it? I will use your little paw to press the button. No, wrong button.